Right. So we have a sample problem. So there are compressed 11.33 cubic meter per minute of an air. So from 26.7 degrees Celsius at 103.42 kPa to the pressure 2 of 827.36 kPa. So we have a given clearance which is 8%. Now, uh, find the isentropic power and piston displacement required for a single stage compression. B. Using the same data, so find the minimum ideal work for two-stage compression when the intercooler cools the air to the initial temperature. And we have your C. So find the displacement of each cylinder for the conditions of part B. Then for letter D, so how much is the heat exchange in the intercooler? And for letter E, so we have to find the overall compression efficiency. So no, sorry, for an overall compression efficiency of 78%, so what will be the driving motor output is required. Okay, so first things first again, so we need to identify what are the given to the problem. So we have the volumetric P1 prime here, volume per rate at 0.1. So that is 11.33. So that will be cubic meter per minute. Then we have the pressure at 0.1 initially, so that will be 103.42 kPa. Then we have for the pressure 2 to be compressed at 827.36. So that will be also kPa. Then we have initial temperature for T1, which is equal to 26.7. No? So I'm going to convert this one to Kelvin already. So I'm gonna add 273 to convert it to make it Kelvin. So we have 299.7 Kelvin. Okay, so let's draw our PV diagram. So I have here your pressure and I have here your volume. Okay. So starting at 0.1, so we have your given. Okay. So starting with your 0.1. So we have at pressure 1. So this is our pressure 1 here. Then this being compressed to pressure 2. Okay. So we have here the pressure 2. Okay, so we have your PB. Now your PBN. So PBN is equal to C. Since the problem is stated that is isentropic, so it's supposed to be we're using commonly we'll be using polytropic, but here so that it will not be the PBN but it will become PBK for your N. So this is now your K. So PB raised to K, so that will be constants where your K is equal to 1.4. So I have here for 0.2. So we have your delivery bulb going at this point. So traveling at this side. So I have here your 0.3. Then going down for the suction. So, okay. So this will become now our point 4. Erase this one. Okay. Then we have here our B1 on this side. Okay. Then we shall have here our Boolean displays BD. Now for letter A, we're looking now for letter A is the isentropic power and the piston displacement. So dalawa yung hinahanap. So we have work isentropic and we're looking also the piston displacement required for single stage. So we're looking for your BD. Okay. Now for your isentropic work, so we have the equation which is equal now to your K. So we have P1, B1, no? So B1 prime. Then it is all over divided by your 1 minus your K. Then multiply to the ratio of the pressure 2 over pressure 1 raised to K minus 1 over your K minus 1. Okay. So for air, we have the value of K that is 1.4. So I'm gonna list down here, which is your given. We have your K for the air is equal to 1.4. Okay. So we have their pressure 1. We have their initial volume for the suction stroke V1. So V1 prime. Okay. So yun, we have that one given. So we have the pressure 2 and ratio pressure 2 and pressure 1. Okay, so we have the K value. So we can solve the problem now directly substituting the equation. So we have 1.4. So that will be multiplied to the pressure 1, which is 103.42. So this is kilonewton per square meter. Then we shall multiply it by the volume flow rate, which is 11.33. So this will be cubic meter per minute. Okay, checking the units again. So that will be okay, it's correct. Then all over divided by we have 1 minus 1.4. So we're gonna multiply this one by the ratio of pressure 2. So our pressure 2, it will be 827.36 and divided by 103.4. So this is our all in kPa units. So it will be cancelled out. Then we have 1.4 minus 1 divided by 1.4. So this is will be minus 1. Okay, so cancel out our common units here. So the square meter will be cancelled out. So kPa, kPa. Then what is left is kilonewton per minute that we have here. So using our calculator, so we have now your work at the isentropic compression, which is equal to negative 300 that is negative 3,327. So this will become now your kilojoule per minute, or let's say that will be equivalent to the conversion. So 55 point negative 55.45 kilowatts. Okay, so we have now the isentropic work. Now for the volume displays, okay, question not again one. So we have your volume displays, which is equal to B1 prime divided by the volumetric efficiency. Or that will be volumetric efficiency with the ratio of volume 1 prime divided by the volume displaced. So rewriting that one, so we have now volumetric divided by volumetric efficiency, where our volumetric efficiency is equal to 1 plus C minus C, that will be multiplied to ratio of pressure 2 pressure 1, then raised to the power of 1 over K, or let's say N. So it will be K. So since we're using is K. Okay. So volumetric efficiency now is 1 plus, so given to the problem, so we have the volumetric efficiency. Oh, sorry. So we have forgot to write here. We have the volumetric efficiency, which is that will be 8%. Okay. So we have 0.08 minus 0.08, then multiply by the pressure ratio. So we have 827.36 kPa all over 103.42. That will be kPa also. Then it is raised the power of 1 divided by the 1.4 for the K value. Now, we have the volumetric efficiency is equal to of the value of volumetric efficiency. So we have 0.7267. So substituting to the equation, so we have now your volume displaced is equal now to your 11.33, so that will be cubic meter per minute. Then divided by 0.7267. Then we shall have your volume displays, which is 15.59. So that will be cubic meter per minute. So looking at the overview of the solution, okay, so we can proceed to letter B. So we can solve now the letter B. Now reading the letter B, so using the same data, find the minimum ideal work for two-stage compression when the intercooler cools the air to initial temperature. Okay, so find the minimum ideal work. So let's try to initially draw our PV diagram here. So we have here at the point 1, no? So I'm gonna write here, this is our P1 at this point. Now I'm just gonna draw a line here. So I don't know what is the value of that one, but I just only try to draw so that we can have the boundaries for your PX, or your intermediate pressure. Then for our final pressure here, our P4. So we try to slice the PV diagram before we have here. So usually we have the hole, no? So you notice here the work. There's only one compression. Now we're going to do a multi-stage. Then I'm gonna slice since we're going to divide the work from here since first stage and second stage must have the same work, equal in work. So I'm gonna draw the line for the isentropic compression of sorry, this is will be yeah, correct, it's isentropic compression. So from 1 to 2, so I have here your point 2 at this point, so this is our point 2. Then we will have an constant pressure intercooling, so this is our px, so it will be at this point. So I'm trying to draw that one. So we have ideally plotting that one here, so we do not know what it will be the volume outcome this one. So just only ideally I'm going to plot this one for your point 3. So w1 2, so then point 3, this point, okay. So first stage, then discharge that one, then I'm going to compress it again for going to point 4. So isentropically I'm going to compress sorry, but that one isentropically I'm going to compress that one, point 4. So I have now our point 4 at this stage. So from here going there, okay. So this is our pressure 4, and this is our px, pressure, intermediate pressure. Okay, so to get the value of px, so remembering that our px, no, or intermediate pressure is equal to the square root of p sub 1 times your p sub 4. Para magkaroon tayo ng value nito. So, substituting, we have the square root of, that will be 103.42 kPa times 827.52. That will be kPa also. Okay. So our px is equal now to, change this one. So our px is equal to how much, using calculator. So we have 292.52 kPa. So we have 292. So I'm gonna write here as the value, which is 292.52 kPa. Okay? So observe nyo rin, no? So supposed to be dapat hindi tayo bumaba ng 103 and hindi ka rin dapat umakyat ng 827. So you must be in the middle between 827 and 103. So take note of that one. So it's one way of checking also. So by plotting the values in the PV diagram. So we have now, let's try to solve now. So since we have given now the work, so we can solve the work now. If you can still remember that the work from the higher and lower stage pressure are must be equal at the same time. So we're gonna multiply the whole equation by 2. So this become now our, but not the total work, but it will become our total work. So I'm gonna change this one to total work. So since we are now, since it is the same, so we're just only using the low stage work, then multiply by 2 should forget the total work of the system for multi-stage. So we have here 1.4 times the 103.42 kilonewton per square meter. Then I'm going to multiply by the volume flow rate V1. So that will be 11.33 cubic meter per minute. So divided by, that will be 1 minus 1.4. Okay. Then multiply by the ratio of P2 for P1. So we have 292.52 divided by 103.42 and raised to the power of 1.4 minus 1 over 1.4 minus 1. So we have now the total work. So I'm gonna multiply this whole equation by 2 to get the total work. So we have value of negative 1,406. So that will be kilojoule per minute. So multiply that 1 to 2. Okay. So we have the total work which is equal now to 2,832. So that will be negative. So this is kilojoule per minute. So let's change this one to we have 1 minute. So we have 60 seconds. Okay. So cancel this one. This one. So we have now kilonewton per second. So it is equivalent now to watts. So we have your work total equal to negative 47.2. So this is kilowatt. So that is the work of the compressor for multi-stage. So let's have a quick comparison of the work for multi-staging. We use the multi-stage or work total there compared to initially the work. So we have 55.4 for the isentropic. Okay, so versus when we do multi-staging, so we achieve work of 47.2 kilowatts. So you'll see the difference, no? That we save. So we almost have a saving of about around 8.2 kilowatts if you will minus mo yung 55.4 kilowatt by 47.2 kilowatts. So nakasave tayo ng mga 8.2 kilowatts sa work, or let's say that will be the work of the compressor. So that is 8.2 kilowatt of electric power consumption. So let's proceed with letter C. So let's find the displacement of each cylinder for the conditions of part B. So displacement. So we're looking now for the uh, BD. So we're looking for the BD of the low pressure stage. Okay, and we're looking now for the volume displacement at the high pressure compressor stage. Okay, so remembering that uh, our volumetric efficiency is equal to B1 prime divided by the volume displaced. Okay, so this will be volume displaced at the low pressure. So we can rewrite our volume displaced at the low pressure is equal to the volume 1 prime divided by the volumetric efficiency. Now we need to solve the new volumetric efficiency since we have the intercooling intermediate pressure, which is your Px will be using, which is equal to 2 point pressure at point 2 and point 3. So for repairing to the figure, so we're looking the volumetric efficiency at the low stage, this side, no? This sides of the compressor. Let's start to, I want to finish this line. Okay, so we have the directions of process nito, ganun. Okay. So we're looking now for this is our low stage compressor, low pressure, and we have your high pressure stage compressor. Okay, so just to put a color para magkaiba naman, then we can solve now. So since we're looking how the volume, if you can see the volumetric efficiency from here going there, so the ratio, um, our volumetric efficiency that will be equal to 1 plus C minus C, that will be ratio of pressure 2 over the pressure 1, so that is raised to 1 minus, 1 over, that will be K. So our volumetric efficiency now equal to 1 plus, we have 0.08 for your clearance, minus 0.08, then multiply by the ratio of pressure 2, which is, at this point, we have 292.52. That will be 292.52 kPa divided by, that will be 103, no? 0.42 kPa. So this is raised to the exponent of 1 over 1.4. Okay. So finally, using your calculator, so we have the volumetric efficiency of 0.9119. Okay. Then substituting that one to our volume displays at the low pressure side. So we have your volume 1 that will be volume 1 prime. So during the suction, we have 11.33. So this is cubic meter per minute divided by mm, the volumetric efficiency, which is 0.911. Okay. Then we have the volume displaced at low pressure. So we have 12.42. So that will be cubic meter per minute. Okay. Now, solving the mass flow rate for, since we don't have, since in the second compressor, so it does not state what is the clearance of the second stage compressor, but we can solve uh, the volume displays the high pressure by means of the equation of uh, so that will be Now we need to, we need to determine the volume flow rate at point 3. So, okay, solutions here. Volume displays the high stage pressure, so that will be equal to uh, volume 3 prime divided by the volumetric efficiency. So we can assume pala they have also, sorry about this, but they have we can assume that they have the same clearance of the piston for it, since magkaiba nga pala sila. So but we can assume that they have the same clearance. Okay. So what we don't have is the volume at point 3. So that will be the suction at this side. So that will be B3. Okay. So para makuha natin yon, we have the volume at point 3 by using your PBMRT prime. So that will be mass flow rate times your R, then multiply by T3 divided by your P3. So, ang wala tayo is yung mass flow rate. So, initially, from the start on, we can compute that one, our mass flow rate from your PB and RT again, mass flow rate. So, we're using the at point 1. So, since we have the given for point 1, and we have the given for T1 also there. So, we can compute the mass flow rate by using the point 1. So, we have the pressure at point 1, so that will be 103.42. So this is kilonewton per square meter. Then multiply that one, so multiplying it by our volume 1, so the volume flow rate at point 1, so we have 11.33. So this is cubic meter per minute. Then I'm gonna divide the whole equation by your R and T1. So our R, that will be 0.28708. So this will be kilonewton meter kilogram Kelvin. Then multiplying by temperature T1. So we have 299.7. So this will be Kelvin. So we can cancel now your Kelvin here. Then kilonewton dun sa taas. This one will be square cancel. And this one also cancel. And also your mass. Okay. Or another meter, sorry. So finally, we have your mass flow rate is equal to 13.62. So that will be kilogram per minute. Now substituting that one in our these equations para, so we have now the mass flow rate, which is now 13.62. So we can compute now for our mass volume 3, substituting that one dito. So I'm gonna write here. So still have vacant here. So our B3 now will be 13.62. That will be kilogram per minute. So I'm gonna multiply this one by your R. So 0.28708. So that will be kilonewton meter per kilogram Kelvin. Then multiply by this one by your T3. So our T3, sorry. So initially our T3 is equal to, so remembering that our T3, no, is equal to your T1. Since the air is being cooled during the intercooling stage, to yung ano rin yung pumasok doon sa cylinder ng first stage. So that's why in T3 is equal to your T1. So we're using 299.7 Kelvin din. Then using the pressure of your intermediate pressure, so that will be 292 then. So for intermediate pressure natin, that will be 292. Since the value of your PX 292.52. So this will be kilonewton per square meter. So cancel that our common units here. So have your kilogram and Kelvin, kilonewton. So I have now your volume 3 prime is equal now to 4.6, 4.0. So 4.006. So that will be cubic meter per minute. So for the volume at the, call this T3, so we have already, so for the volume display, so we can solve now our B3, which is 4, so 4.006, so that will be cubic meter per minute. So I'm going to divide this one by your volumetric efficiency, which is 0.9119. Then finally, we have the value of, for the volume displaced at the high pressure, which is 4.393. So that will be cubic meter per minute. So comparing siya doon sa initial natin na volume displays. So we have 15, 15 no? Initially we have yung volume displays at the low stage. So, oh, this is, sorry. At the low stage, we have the volume displays, which is 12.42. Now, at the high stage, so we have the volume displays of equivalent to 4.393. So let's take the overview ng solution natin. Okay. So, yan, yung for the solution for letter C. So let's proceed to letter D. So let's go to letter D. So how much heat is exchanged in the intercooler? So for the intercooler, we have your Q. So that will be the mass flow rate, no? Times the Cp of air at a constant pressure. Then we have the change in temperature T3 minus your T2. So meron tayong mass flow rate and we have this Cp at a constant. Now, T3, since this is during intercooling, so we cool down the air. to an initial state which is equal to the T1, which is our 299.7. Now what we don't have is T2. Okay, so since we are in isentropic compression, okay, so we can use the isentropic process. So we have your T2, T1, which is now equal to the ratio of your using PBT relationship, P2, P2 over P1. So we have your K minus 1 over K. So we have your T2 is equal to T1 times the ratio of pressure, which is, this is when your P2. I forgot. So our T1 is 299.7 Kelvin, and we shall multiply this one to the ratio of pressure 292.52 TPA divided by 103.42 TPA. Then raised to the power of 1.4 minus 1 over 1.4. So we have now the value of your T2, which is 403.36 367, or let's say this is 404. So this is 404 Kelvin. So we can now directly solve the. Okay, so let's substitute now to the equation. So we have your mass flow rate, which is 13.62. So we have here the mass flow rate at 0.3. No? So that will be 13 at the. So the mass flow rate of the system, we have 13.62. So this is kilogram per minute. Okay. So I'm going to multiply that one to our CP of air. That would be 1.0062. This is kilonewton meter per kilogram Kelvin. Then multiply the change in temperature. So we have 299.7 no? Minus 403.4. So this is Kelvin. So cancel out the units. So this one cancel out. So kilogram. Okay, so we have your Q. The intercooler is now equal to negative 1421. So this is kilojoule per minute. So take note, negative sign, so indicate that the work is being supplied and heat is being produced by the system. Okay. So letter E, what will be the overall compression efficiency? What will be the overall compression efficiency of 78%? So what will be the driving motor is required? Okay, so for the compressor efficiency, so this is yung tinutukoy niya dito, that is called it mechanical efficiency. So our mechanical efficiency, that will be equal to work indicated, that is work inside the work produced by the cylinder, then divided by the work brake or the work of the shop. So what we'll need is the work of the brake or work of the shop. So work of the brake or work of the shop now is equal to indicated work divided by the mechanical efficiency. So our work brake indicated work, that will be 47.2. So this is kilowatt divided by the mechanical efficiency, which is 78%. So we have 0.78. So we have now your work break or work of the shaft is equal to 60.5 kilowatt. Okay, so that ends our solutions. So checking out the overview of our solutions here. What are the problem? Okay, so we started here. Okay. So that's it.